Ladies and gentlemen, welcome to my lecture on Fama MacBeth Regressions. First of all, I would like to thank you for your positive feedback for my last lecture where I've been discussing Fama MacBeth Regressions. And now I would like to talk with you how to implement Fama MacBeth Regressions using the so-called Shanken correction. So one of my YouTube followers recognized that the previous approach of Fama MacBeth regressions had a bias, and right so. The previous approach that I discussed with you did not take into account that the betas are estimated. And the way how we implemented the Fama MacBeth regressions did not take into account that there might be a bias. Given that we have a very large sample, however, let's say we have 10,000 observations, we know that the OLS estimates converges towards the true value of beta. Yeah? So if we have a very, very large sample, okay, this bias becomes smaller and smaller and smaller. In real life, however, we have finite samples. Yeah? Let's say we have the S&P 500 and we consider 50 years of data. That leaves us with 50 times 12, which is 600 observations. First of all, the question arises, when do we need Fama MacBeth regressions anyways? So one example is if we have more assets than we have time series observations. Yeah, so let's say in the US we have about 4,000 to 4,500 stocks, but if we use data from the 1960s onwards or the 1970s onwards, let's say we have 50 years of data or 60 years of data corresponding to 600 to 660 observations, so we have more cross-sectional assets. So the cross-sectional dimension is larger than the time series dimension. In this case, it could make sense to use cross-sectional regressions like this Fama MacBeth approach. Another example, let's say we have a time series of T observations, and for some of the assets that we consider, we have only, let's say, for a certain subsample observations. So what we can do then is we can estimate the corresponding beta, the factor exposures for these assets given the time series that we have available. Yeah? So we can get our beta estimates even for different time windows. Okay? So that's also a situation in which Fama MacBeth regressions could make sense, because if you would estimate, because you cannot estimate this in a time series regression framework using the GRS test. So these are the situations in which Fama MacBeth regressions make sense. Okay. For instance, one example is that comes to my mind is hedge funds. Okay, so if you want to investigate hedge funds, you have a sample, and we know that hedge funds usually are very restricted in what they report, and they have you will probably not have time series observations for the whole sample, yeah, but you have only for certain subsamples observations for each hedge funds that you consider. So what you can do then is you can, for each time window, you can estimate the factor loadings. Yeah, you can make subsample regressions, yeah, and then collect the betas, yeah, across the assets. Yeah, so this would make sense. So what are Fama MacBeth regressions about? So what's the idea? So the idea is, yeah, let's say we have capital N assets, yeah, capital N assets. So that's our cross-sectional dimension, yeah, capital N, and for each asset I, we want to describe the expected return of the asset I in excess form by a linear combination of the factor exposures, yeah, and we do this for all capital N stocks. Yeah. So what we want to figure out is there a common risk premium for each of these risk factors? Yeah. If so, then the lambdas, so the exposures against the factor exposure, beta, should be statistically significant. Yeah. So the difference between the cross-sectional regression and the time series framework is very simple. So let's say we have a time series framework, yeah, where we have a variable yt, and we say, okay, yt should be dependent on some x variable, yeah, let's say beta 1 times x1t plus beta 2 times x2t, and we have here an error term epsilon t. So we want to describe, so in the time series framework, we want to describe the variation of the yt variable in the time series by the variation of the x variables. And in this case, we have two, x1 and x2. The corresponding beta, if the beta is significant, then it means that the variation in our x variables describe, or they explain the variation in our dependent variable yt. That's in the time series framework. In the cross-sectional framework, it's quite similar, but here we want to describe not the time dimension t, we want to describe the cross-sectional dimension I. Yeah, by what? By the variation of the betas. So the betas are our independent variables, okay? And what is here, the factor exposure, is in the cross-sectional dimension, the lambdas, okay? So if the variation of the betas explain the variation in the expected returns of our test assets, then we would expect that the lambdas are statistically significant. Okay, so that's our null hypothesis model. Yeah? So that's our null hypothesis model, which you want to test. That's the basic idea of the Fama MacBeth framework. Okay, so and what you see is we don't have an intercept term here. Yeah? So we estimate this model under the null hypothesis, and that's why we do not include here an intercept term. Yeah. So what do we have to know in order to be able to implement Fama MacBeth regressions? We have to know basic econometrics. Okay, so we have to know the basic OLS, ordinary least squares estimation technique, which I assume you are familiar with. So in vector notation, if we use a model, linear regression model, we can describe it in vector notation. Yeah, the vector of dependent variables yt in standard vector notation, y, let's say y is a t by 1 vector, is described by a regressor matrix x, okay, times the vector beta, where we collect the factor exposures, and an error term u, where u, of course, has the same dimension like our y, so it's t by 1 vector, and beta is a k. Let's say we have k risk factors and a constant, then this guy here has a dimension k plus 1 by 1, and this guy here has a dimension t by k plus 1. Okay, so very simple. So using this simple linear regression framework, we can easily estimate the point estimator beta. Beta hat is then simply given by x transposed x inverted times x transposed y. Very simple. We also know that we can get the estimated residual vector. How? Well, simply by forming, we have to reformulate this equation here. We put this guy here, x times beta hat on the other side, and what we get then is that our U hat, the estimated residual vector is what? Well, it's Y minus the regressor matrix X times the estimated vector of point estimators beta hat. Yeah, so very simple. So that's what we have to know before we can get started with Fama MacBeth regressions. So then let's say we just as a showcase, we want to investigate whether the Fama and French 5-factor model, if it's able to explain the cross-section of expected returns. Yeah? That is Finance 101. So we know the 5-factor model. What do we have? So we have the market factor, we have the size factor, the value factor, we have the profitability factor, and the investment factor, right? All of these risk factors are zero-cost strategies. Yeah? So that is important to know. So these are zero-cost strategies. Yeah? So, and the test assets that we use in this framework have to be in excess form. So from each time series vector of test assets, we have to subtract the risk-free rate in order to operate with Fama MacBeth regressions framework. So let's say what is standard practice in finance. So usually what many people are doing is they use the 25 portfolios sorted by size and book to market ratio, or size and investment, or size and profitability, or whatever. They use these 25 Fama and French test portfolios in order to test the pricing models. Yeah? This is standard practice. You can get the data from Kenneth French website. Okay. So let's say we want to investigate this issue. We download 25 test assets, yeah, and our test assets are denoted as Y. And now you have to remember the test assets are in excess form. So our Y1t are the excess returns of our asset 1 at time t. Okay, and this test asset can be one of these 25 portfolios sorted by size and book to market ratio. So test asset 1 is, for instance, a portfolio of small stocks that have a high book to market ratio. Okay? So we have these, we start with a time series framework. So that's the first step in Fama MacBeth, in implementing Fama MacBeth regressions. We start with the time series dimension. Okay? So we describe the evolution of the excess returns of asset I at time t by a constant term, the alpha, yeah, which gives us the pricing error in the time series framework. Okay? But we are not interested in that now. But anyways, in order to estimate the betas in the time series framework properly, we have to include here an intercept term. Okay? So Y1t, the excess returns of asset 1 at time t, is given by alpha 1, which is the intercept term, plus beta 11 times x1t, and x1t is now what? It's the market factor in excess form at time t, plus beta, beta 12, which is the exposure of the first test asset against the second risk factor, beta 1t, exposure of the first test asset against the second risk factor, times x2t. So the second risk factor in the Fama and French model is obviously the size factor. Okay? So, and so on, until we end up with the last risk factor, which is, and it enters the equation by beta 15, which gives the exposure of test asset 1 against the fifth risk factor. And the fifth risk factor is the investment factor, right? So x5t is the investment factor, okay? And plus, we also have to include a residual term, an error term, yeah? That gives us the idiosyncratic part of this equation here, okay? So U1t measures the error for the first equation, yeah? We move on. We have also a second equation for the second test asset, and it has exactly the same shape. So of course we have the same risk factors here. Yeah, in each equation we have the same risk factors, of course, but we have different factor exposures. Yeah? So the betas of the second test asset here, the exposures of the second test asset against our risk factors x1, x2, x3, 4 and 5, the corresponding betas will be of course different from the betas of the first test asset, okay? So we have 25 equations given that we have 25 test assets. So n is 25 here in this case. So for the 25th test asset we have this equation here, of course. Yeah? Now we have to remember that each equation can be given in vector notation as well, as we have discussed here. Okay, so this guy here, yeah, is a t by 1 vector. Yeah? So it's the asset 1. Yeah? If I is 1, this guy here becomes a 1. So it's our yi, and I is from 1 to 25. Every vector in this equation framework is in vector notation a t by 1 vector. Yeah? What we see also is that the regressors here are always the same. So we use the same regressor matrix in each equation, of course. So we can if we use vector notation, what is our x then? In this case here, it's obviously a t by 6 matrix. We have capital T time series observation for each single risk factor. So here in the first column, our x11 is measures the excess return of the market factor, which is our first risk factor in the Fama MacBeth 5-factor model, at time 1. x21 is the excess return of the market factor at time 2. And xt1, of course, is the corresponding excess return of the market factor at time capital T. Yeah? And in the same manner, obviously, this x12 gives us the return of the size factor at time 1. x22 is then analogously the corresponding return of the size factor at time 2, and here capital x at time capital T2 is obviously then the return of the size factor at time capital T. And in the same manner here, if you consider the last column here, of course it gives us the corresponding returns for the investment factor. So it collects the returns of the investment factor in a t by 1 vector. Now we stack the time series vectors in a matrix. We add a vector of 1s, which gives us in the regression framework obviously corresponding point estimates for the alphas here. That's why we have a t by 6 matrix, which is k plus 1. Again, k is the number of risk factors in the Fama MacBeth 5-factor model. Capital K is 5. Hence, our X matrix has the dimension t by 6. So once we have defined our matrix, so we use in each estimation, for each test asset, this guy here is varying, obviously. For each test asset we have a different time series vector of excess returns, but this matrix here of risk factors is always the same. If we use the standard estimation technique of OLS, we will get obviously in each estimation for each test asset we get a different vector of betas. So the next step in our Fama MacBeth regression framework is that we do 25 times the following regression. So we regress the vector yi for each test asset on what? On the matrix of risk factors X that we defined previously. Remember that our X matrix is a T by 6 matrix, and each vector yi is a T by 1 vector. So what we get from our OLS regression, we get the point estimator for each asset I, and it's the corresponding dimension of the point estimator is 6 by 1. Remember that we have an intercept term, so this first element here in this vector is actually the corresponding alpha hat, okay, of asset I. So this beta 0I here in this notation gives us the corresponding point estimate. It's actually the same like this alpha hat I. Okay. So the dimension of this beta hat estimate for each iteration is k plus 1 by 1, and k is 5 because we have 5 risk factors, so the dimension of this vector is 6 by 1. Okay? It is now important to note that we are not interested in this cross-sectional framework, we are not interested in the pricing errors measured by alpha hat. But we are only interested in the exposures against the risk factors, which are given here, our beta 1 to beta 5. So recall that our beta hat 1 gives us the exposure against the market factor, because the first risk factor is the market factor in the Fama and French 5-factor model, whereas the fifth risk factor, the beta hat 5, gives us the exposure of asset I against the investment factor. Okay, so we are only interested in the exposures against the risk factors, the 5 risk factors. So what we have to do is we have to grab this subvector, which has a dimension 5 by 1. We have to transpose this guy and put it into a matrix that we denote a capital B hat. Okay, so each element here, we put it here in this matrix. Okay, so this is for our first regression, for the first test asset. We will find it here in the first row of that matrix capital B hat. In the next iteration, if we do the same regression here, but for the second test asset, when I is 2, we get a corresponding vector of factor exposures of the second test asset. Again, we grab the corresponding point estimates from that vector and put it here in the second row of our matrix capital B hat. Okay, so we do this for each test asset. Here we have the test asset I is 1, second row for the test asset I is 2 for the second test asset, and so on. And here the last row gives us the corresponding point estimates against the 5 risk factors for the 25th test asset. So recall that all of these are estimates, so we operate with estimates here, so that's why we have this hat everywhere. What else do we do? Remember now that we discussed that from our OLS regression framework, once again, y is given by x times beta plus u. From that equation, it follows that this u hat is given by y minus x times beta hat. So for each equation, for each regression equation, we also get the corresponding estimated vector, u hat, of regression residuals. So what we can do then is we can stack them into a matrix. We can collect for every regression of these 25 regressions. We can collect the vector, the corresponding vector of regression residuals, and stack them into a matrix that we denote as E hat, capital E hat. So in the first iteration, when we do this OLS regression for the first test asset, yeah, we get obviously this vector here. Yeah, it's a t by 1 vector. Yeah? Recall that in the time series framework we have capital T observations. Yeah? So obviously our U hat then must be a t by 1 vector. Yeah? We stack it here, yeah? And we do this for each test asset. In each regression equation for each test asset, we stack the corresponding vector here step by step into this matrix here. Okay? We can easily code this in a for loop in a program called MATLAB, and this is what we will do soon. Okay? But it's important to note that we have to store the corresponding residual vector, yeah, iteratively in this matrix capital E hat. As a consequence, this matrix here must have the dimension capital T by 25, because we have, first of all, 25 test assets. Yeah? In each column, we have the residual vector of each test asset, and we have from row 1 to capital T, yeah, we have the corresponding time series observation. The next step in the Fama MacBeth framework is that we estimate the covariance matrix of the risk factors, which we have denoted here as sigma capital F. Okay, so how does it look like? Well, the covariance matrix is symmetric. On the main diagonal, we have the variance of each single risk factor, since we have 5 risk factors in the Fama and French 5-factor model. Yeah? So we have on the first element here in this covariance matrix is the variance of the market factor in excess form, and the last element, the 5th element, is the variance of the investment factor. Yeah? So the covariance, so the element 1, 2 is the covariance between x1 and x2, which gives us the covariance between the market factor and the size factor, given that x2 is the size factor and x1 is the market factor, and so on and so forth. Okay, so obviously the covariance matrix of the risk factors is a 5 by 5 matrix. It's a k by k matrix. And since we have 5 risk factors, it must be 5 by 5. So we can estimate each single element here very simple. So obviously what we have here is that each element, so the covariance between the market factor and the investment factor is the same as the covariance between the investment factor and the market factor. So every element here has the same entry, the same number. Okay, so given we have the 5 by 5 matrix, what we have to do is actually we have to estimate 5 times 5 is 25 minus the element on the main diagonal, which is 5. So we have 20 covariances that we basically have to estimate here. So what's the covariance? So very simple. Yeah, we know this from basic statistics. The covariance between xi and xj is given by 1 over t. Sum from t is 1 to capital T from what? From risk factor xit minus the mean from xi times what? Times xjt minus the mean from risk factor xj. Denoted here as xj bar. So actually we have to estimate it. So each of these single elements here, well, we have to plug in the corresponding time series vectors. But luckily MATLAB has a function, or it's just, you have just to write cov, C-O-V, from what, then you have to write the matrix from what you want to compound the covariance matrix of, and then MATLAB gives you the corresponding covariance matrix. So we don't have to do this anymore by hands or with a loop. We can just code it directly. So we don't have to bother with that. But this is one input matrix that we need in order to compound the t statistics of our lambdas here. Okay, so that this is just one increment. The next step, the third step here in our procedure, is we have to estimate also the vector of expected returns. Given that we have 25 test assets, capital N is 25, so our vector of expected returns must be then a 25 by 1 vector. And each element here, the first element is y1 bar, that's simply, it's 1 over t, sum from t is 1 to capital T from what? From our test asset, from the excess return of test asset y1 t. That's very, very simple. So we have to do this for each single element here, for each single test asset in excess form. We have to compound the time series, simple time series average, and stack it here in this vector. This is very simple. We can easily do this in a very short for loop. So the next step in this estimation procedure is to get the risk premium vector lambda. Since we have 5 risk factors, this lambda hat, our estimated vector of risk premium, is or must be a 5 by 1 vector. Okay? So, and it's very simple. So our lambda hat, so the vector of estimated risk premiums, is given by our matrix capital B hat that we defined earlier, transposed times itself, inverted, times capital beta hat transposed, times the vector of expected excess returns. Okay? So what we know is this vector here has a dimension 25 by 1, and our beta vector has the dimension 5 by 25 because it's transposed, right? And we know that our beta hat, capital B hat matrix has a dimension 25 by 5. So here it's transposed, so it's 5 by 25, and now the dimensions are correct. Okay, so a matrix, a 5 by 25 matrix times 25 by 5 matrix becomes 5 by 5. Okay, multiplied with the matrix that has a dimension 5 by 25, so what comes out here is 5 by 25 that has the dimension 5 by 25, and we multiply this expression with something that has the dimension 25 by 5, so what comes out has the dimension 5 by 1. So the vector of the vector of risk premiums lambda hat. So we have here the lambda hat 1, which is the risk premium that is related to the variation of the betas against the market factor. Then we have the lambda hat 2, which is the corresponding risk premium that is related to the variation in betas against the size factor. And so on. And the lambda hat 5, which is the corresponding risk premium related to the variation of the betas against the investment factor. So the question arises, are the risk premiums statistically significant? So we want to get the t-statistics. So, and in order to get the t-statistics for our risk premiums, because these are just the point estimates, we still do not know if the corresponding variation, the cross-sectional variation in the betas, do they really matter? The point estimates do not give us the information. Okay, so if you want to know if they are significant, we need to get the corresponding t-statistics of our point estimates. So how do we proceed? So first of all, in order to, so we are interested in what? We're interested in the covariance matrix of our risk premium vector lambda hat. Yeah? So, but what do we need more in order to compound that? We need also another increment, and that's the covariance matrix of the residual vector. In previous step, we already discussed that we have this, that we constructed this matrix capital E hat. So we remember that has a dimension. This is a T by 25 matrix, right? So if we compound the covariance matrix of our matrix capital E hat, which stacks the residual vectors into this matrix here, so the corresponding covariance matrix must have the dimension 25 by 25. Because we have capital N is 25 test assets. Okay, so the corresponding covariance matrix, how does it look like? So again, like in the previous case with the factor covariance matrix, it's very similar here. So on the main diagonal, we have the corresponding variances. We have the first element is the variance of the residuals for the first test asset, and the last element on the main diagonal of that covariance matrix is the variance of the 25th test asset. Yeah? So element 1, 2 in this matrix here is the covariance between the residuals between the first and the second test assets of the time series regression. Okay, so that is how the matrix looks like. Again, we don't have to compound it by hands, so we can just write covariance, give me the covariance of that matrix, and any program, especially MATLAB, will give you immediately the corresponding covariance matrix of our capital E hat matrix. Yeah? So we need that guy as well. So now we have all the increments that we need. Yeah? So we have defined our matrix capital B hat in an earlier step. We have defined the matrix sigma F hat, which is the covariance matrix from our risk factors. We have defined it in the earlier step. Moreover, we have also defined now the corresponding covariance matrix sigma E, capital E. So we have now everything that we need in order to compound what we have denoted here as sigma from lambda hat. It's an estimate. It's the estimated covariance matrix of our residual vector. Because our residual vector has a dimension 5 by 1, since we have 5 risk factors in the model, this covariance matrix, the corresponding covariance matrix of that vector of risk premiums must have the dimension 5 by 5 or k by k. Because we have k risk factors. Okay? So, and this is how the formula looks like. Yeah. So we can't go through it, so we have to write it down. So the covariance matrix is defined as, first of all, we have to multiply everything with the factor 1 over capital T. Yeah? And moreover, so we have to, it starts with our capital B hat transpose times itself inverted, times our matrix capital B hat transposed, times our covariance matrix of the residual vectors, which we have defined here, times our matrix capital B hat, then in parentheses times capital B hat transpose times itself inverted, and then we multiply this expression here, with the so-called Shanken correction, which is given here in the blue parentheses. So what is that? So it starts with 1, that's just a number, it's just a factor 1 plus what? Well, that's the vector of lambda hat transposed. Lambda is a 5 by 1 vector, lambda transposed is a 1 by 5 vector, right? Times the covariance matrix of our risk factors sigma f hat inverted. Yeah? So we have to invert the covariance matrix. The covariance matrix is symmetric, yeah? And the covariance matrix of the risk factors has the dimension 5 by 5, and so does the inverted covariance matrix. So the dimension here is 5 by 5, and again we have to multiply this product here with the corresponding vector of risk premium to lambda hat, so which has a dimension 5 by 1. So what we get out of here, if you multiply this out, that's just a scalar. It's 1 by 1. So, and probably or most likely this is larger than 1. Or sorry, it's larger than 0, right? It must be, it's usually larger than 0. Because if this would be 0, we wouldn't need the Shanken correction, right? So the Shanken correction, this term here, this gives us, this accounts for the uncertainty in the estimated betas. Okay? So what does it mean? So because this is most likely larger than 0, so we multiply this term here with something that is larger than 1. Okay, so it means that the covariance matrix becomes bigger. In turn, because the covariance matrix becomes bigger, the t-statistics become lower. Okay, so that is basically how this Shanken correction works. So it accounts for the additional uncertainty. Yeah? And if we account for the Shanken correction, yeah, when estimating the corresponding covariance matrix of the estimated risk premiums, then the covariance matrix becomes larger. Okay, and therefore, because the covariance matrix becomes larger, there's more uncertainty. The t-statistics become lower. So the significance, so it's less likely that one of these beta variations has a significant explanatory power in describing the cross-sectional expected returns. Okay. So what else do we have? So we have to add the covariance matrix of the risk factors here, yeah, in the end of the equation, yeah, which is here, our sigma capital F hat. Yeah. So everything we can simply put into MATLAB. Yeah, it looks much more fancy than it actually is. Yeah, you can just, we have defined our matrices beforehand. We just plug it into the system, and what MATLAB will spit us out is the corresponding matrix that has the dimension 5 by 5. Yeah, so it is a 5 by 5 matrix, which has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Estimates. Okay. So what do we have to do? So if we want to get now the corresponding t-statistics in the sixth, which is the sixth step here, the corresponding t-statistics for a risk premium. Let's say we want to have the t-statistic for the first risk premium, our lambda 1 hat, which is the corresponding risk premium for the market factor. What do we have to do is we have to grab the first element of our risk premium vector, yeah, this lambda, the corresponding estimate for lambda 1 hat, and divide it by the corresponding element on the main diagonal of that matrix here. Yeah. So, which is then obviously given by this element here, yeah, which is the variance of our lambda hat 1. Okay. When we can, so obviously only the elements on the main diagonal matter. Okay, because here we have the variances, the corresponding variances for our estimated risk premiums. Yeah. So if we want to get the t-statistic for our for the risk premium that is related to the investment factor given by lambda 5 hat. So we grab the fifth component, the fifth element of our vector lambda hat, and divided by the square root, by the square root of the fifth element that we have here. So it's a very simple. So by that, we get the corresponding t-statistics for the risk premiums. And we know that from standard statistics classes, if the risk premium is larger than 1.96, given we have a 5% level, we would argue, or we would conclude, that the corresponding risk factor is statistically significant on a 5% level. Finally, the question arises, is the model correct? Is the Fama and French 5-factor model capable of pricing the cross-section of expected returns correctly? This is which we assume under the null hypothesis to be true. So, is the model correct? So how do we proceed? Recall now that we do not have any intercept term here. So, given that, we can estimate the pricing errors as, and denoted here as alpha hat, as what? So we have the vector of expected returns of our test assets. We have this already from previous step. That's a 25 by 1 vector, capital N is 25, and we subtract what? The corresponding regressor matrix, which is in the cross-sectional regression denoted as capital B hat, times the vector of risk premiums lambda hat. So we know that the matrix, the regressor matrix, the cross-sectional regressor matrix, capital beta hat, has the dimension n by 5, where we know that 5 is k and n is 25. So this is the dimension is 25 by 5, whereas the vector of risk premiums lambda hat has the dimension 5 by 1. If we multiply this out, we have the dimension 25 by 1, so that's a 25 by 1 vector. So we subtract from a 25 by 1 vector something that has the dimension 25 by 1, and what we get is a vector of pricing errors that has the dimension 25 by 1. And you see already, for those of you who are familiar with econometrics, we see already the similarity here from this expression. Let's take the blue pen. So it's very similar, like the u hat is given by y minus x times beta hat. So that's basically the cross-sectional counterpart from our time series framework, where we have the residual vector, and we get it by subtracting the estimated y hat. This gives us here, this term is nothing else but the estimated vector y hat, and we subtract it from what? From the original vector y. So, and this gives us the errors of the time series equation or regression. And this is the counterpart for the cross-sectional regression, but it's very similar, you see. So what we get here is if we subtract the estimated pricing errors from the, or we estimate the estimated vector of cross-sectional expected returns, which is this, basically. This gives us the expected returns estimated by the model, and we have to subtract this from the real vector of cross-sectional expected excess returns. Okay, so the difference is the pricing error of our model, and this is what we denote here as our alpha hat. So we know from statistics that if we multiply, so this expression here, our pricing errors transposed times the inverted covariance matrix of the pricing errors times the pricing errors follows a chi-square distribution with n, capital N minus capital K degrees of freedom. Recall that our n is 25 in our case, and capital K is 5, so we have to compare. So our test statistics follows under the null hypothesis a chi-square distribution with 20 degrees of freedom. Okay, so we know already what our vector alpha hat is. Yeah, we have defined it here. Yeah, we have all of these increments here already estimated earlier, so we can easily get the vector of pricing errors, but we have still to estimate the corresponding covariance matrix, which has to be here in this equation inverted. Okay, so what's the covariance of our pricing error vector alpha hat? This is what we see here. It looks huge, okay, but it's actually, you just have to plug it into the system and our computer program will estimate it. But we have to know what we do. So the covariance matrix of our pricing error vector alpha hat is given by 1 over capital T times what? So what we have here, it starts with an identity matrix, which is a matrix, you know that from statistics. It's a matrix that has only ones on the main diagonal and zeros anywhere else. Okay? And the dimension of this identity matrix here is n by n. So it's a 25 by 25 matrix. 25 ones on the main diagonal. Very simple. So we subtract this matrix from what? So we have here capital B hat times, in parentheses, capital B hat transpose times capital B hat inverted times capital B hat transposed. This is the expression in the first parenthesis here. We have to multiply that with what? With the covariance matrix of our E matrix. And remember now, that's the covariance matrix of our where we have stacked the vectors of our time series residuals. So this matrix here has the dimension 25 by 25. You might remember that from the previous step. So we multiply this in turn with the same expression that we have here, but we have to transpose it here. You see, we have the transpose sign. So, and then again, we have to account for the Shanken correction. So, which we see here, and it is the same expression that we had in the earlier step. So we have here something. We start with 1. If this guy here would be 0, then it would be simply this term here. Okay. So the covariance matrix of the pricing errors would be simply given by this term here. But once we account for the uncertainty in the estimated betas here, from the time series framework in the first steps, we have to account for the Schengen correction here, which is 1 plus the vector of risk premiums transposed, which is 5 by 1, transpose is 1 by 5, okay, again, so it's 1 by 5, times the inverted, the inverse of the covariance matrix from the factors, okay, that's 5 by 5, and we multiply it with the simple vector of risk premiums, lambda hat. So what we get out of here is just a scalar, it's just a number, it's a 1 by 1. So and it's probably larger than 0. So again, this guy here, because of the Schengen correction, the covariance matrix becomes larger. Once we account for the uncertainty in the estimated betas. So what comes out here, is obviously a 5 by 5, a 25 by 25 matrix. So you can check the dimensions. Recall that this guy here is n by n, so it's 25 by 25. And we multiply it here with something that has also here, because this is transposed. So what is here has also the dimension 25 by 25, and we multiply a matrix that has a dimension 25 by 25 with a number that is larger than 1, Yeah, and we know from basic linear algebra, if you have the matrix A times a factor times a scalar, yeah, let's say 2.3, yeah, the dimension of what comes out here is the same like the matrix alpha A. Yeah? So multiplying a matrix with a scalar doesn't change the dimension of the matrix. Okay, very simple. So once we have estimated the covariance matrix of the pricing errors alpha hat, we can plug in everything here in this formula. Yeah? That's our test statistic. Okay, what we get out of here, yeah, is simply a number, of course, because this is the vector alpha hat has the dimension 25 by 1. Transpose is 1 by 25 times something that has a dimension 25 by 25 times 25 by 1 is 1 by 1. Okay, so what comes out here is just a number. And this number we have to compare with the critical values of the corresponding chi-square distribution with n minus k degrees of freedom. Okay, since we have 20 test assets, so the corresponding reference distribution is a chi-square distribution with 20 degrees of freedom. And we know from statistics, the chi-square distribution, it looks different from the normal, so it has a longer tail here, yeah? So, and we have to figure out, so what's the 95% probability, okay, for a chi-square distribution with 20 degrees of freedom. Once our test statistic gives us a number that exceeds this corresponding critical value, yeah, we would reject our model. In this case, we would conclude, well, our pricing model cannot price the test assets correctly. Given that this estimated number here would be below the critical value of the chi-square distribution with 20 degrees of freedom, yeah, once it's maybe here in this area, then we would not accept, then we would not reject this model. Then we would say, okay, the pricing errors are statistically jointly not different from 0. Therefore, our pricing model here appears to correctly price the cross-section of expected returns. And what we will do and what follows now is we will implement this methodology in MATLAB. And hopefully you made your reading notes so that you can compare step by step what we have been deriving here on the whiteboard with what we do now in MATLAB. Ladies and gentlemen, welcome to my lecture on Fama MacBeth Regressions. What we will do now is we will implement what we have derived on the whiteboard in a computer program which is called MATLAB. And of course, you can use any program that you would like to use, but in this course I will show you how to implement this methodology using MATLAB. Why MATLAB? You might wonder, well, I believe that that MATLAB as a program is very user-friendly and it's very easy to use once you know the corresponding matrix algebra and econometrics that is required for this course. When you open MATLAB, this is basically the user surface. This is what appears once you open the program. What we will do now is we will open a script. Everything what we could do, we could basically write it here in the command window, what you see here on the right hand side, but we'll open a new script by just pushing this button, new script. And what pops up is then an empty page, like a Word document basically. Everything what you write here is not directly copied into the command window. What we will do is we will write first the code ready, and then we will copy everything into the command window, or we can just run the code. It depends. Everything, any matrix that we define here will appear on the left hand side in the workspace. So everything what is done here in MATLAB every matrix that is defined in the command window will appear here in the workspace. And here we can basically then just double click and check if the matrix is correctly defined. So let's go back here. I have opened two of these scripts, obviously, so I will close one of them. Yeah, so now I have only one script opened here. So first of all, let's have a look at what we have to operate with. I have made a file here on my computer, on my desktop, and it's denoted as Fama MacBeth Shanken. And what we'll see here is here are two matrices, yeah, in Excel. If we double click the first matrix here, it's called 25WV, which means value weighted size and profitability portfolios, yeah, for the European market and in gross terms. So this is a matrix given the returns as gross returns. If we double click on the Excel file, yeah, let's just have a look at how it looks like. That's how it looks like. Yeah, very, very easy. So we have 25 portfolios here. Yeah, B1 to here to Z. So 25 assets we have here. Each column, yeah, each column vector are the gross returns of one asset. Yeah, the assets here are sorted by size and profitability, and the test assets are value weighted. And we use the European market. So that's important to bear in mind. Our data sample starts in July 1990 and goes until September 2019. Yeah. So why do I use this data set? It's just for illustrative purposes. And in one of my forthcoming papers, I'm reinvestigate the Fama and French 2018 papers entitled Choosing Factors. I examine basically the asset pricing implications of the Fama and French six-factor model in the European market, among others. Yeah, I investigate the European market, Asian Pacific market, excluding Japan, the Japanese market, and the market in North America. Yeah, and the sample starts in the 90s. Yeah, so I use basically the same data set that I used in my own research. Yeah, so we have again 25 test assets that we would like to test using Fama MacBeth regressions. We want to investigate whether the five-factor model is priced in the cross-section of these 25 test assets sorted by size and profitability in the European market. So as you see here, we have 351 observations here, yeah, time series dimension that we denoted in the lectures as capital T is 351. Okay, so that's the data matrix of test assets. We also have here a data matrix of risk factors that I have denoted here as Europe underscore risk factors underscore small FF5, Fama and French 5-factor model. Okay, let's open this actual sheet as well. So what we see here is a data matrix. Of course, it must have the same dimension as the other matrix. So what we have here is, so we see here is we have in the first row we have the notation here what the data vectors are. So in the first row we have the market factor in excess form. It's for the European market again. These are European factors. It's the European market factor minus the risk-free asset. Okay. We have in the second column the size factor. We have the value factor here in the third column. We have then the profitability factor, robust minus weak, and the last factor here is the conservative minus aggressive investing stocks. This is the investment factor. Okay. So what is now important to note is I don't use for these factors here, the value factor, profitability factor, and for the investment factor, I do not use the standard Fama and French factors for the European market, but I'm using small spread factors. Okay, so I basically use only small stocks to implement the value factor, profitability factor and investment factor, and I want to investigate the asset pricing implications of small spread factors. Yeah? So it's the same thing. If you have read the paper from Fama and French, the 2018 paper, they talk about that small spread risk factors, that they basically perform better than the standard risk factors that take into account the whole stock universe. Yeah? So I conditioned my thoughts here on only small stocks. Yeah? So the spreads are wider. Yeah? Here in the last column, I have the risk-free rate for the European market. Yeah, we can also plot some time series. Let's plot the first time series here together with the timeline. We go and insert. Then we choose here this plot. So these are the excess returns of the market factor. Very simple. And we can also plot the same time series for the size factor, or maybe we can take both the market and the size factor depending on time. Let's plot this two time series. Yeah, and this is what you see here. Yeah, so you see from this graph that the volatility from the size factor, even though we are using only small stocks, you might think that the volatility is much higher than the market factor volatility, but this is not what we see here. Okay, so you see that the size factor, even conditioned on small stocks, seems to be less volatile than the excess returns of the market factor. So once again, we have to take into account that using the Fama MacBeth framework, if we use zero cost strategies, risk factors that are zero cost strategies, long short strategies, as risk factors, then we have also to use test assets in excess form. Otherwise, obviously, we cannot use this methodology. So let's go back again here into our MATLAB window. We have here our script. Let's import the data. We go here on data import. Let's import first the test assets. We make double click on that, and then MATLAB opens this wizard, this import wizard. Everything seems to be all right. Everything is accounted for in the data matrix. Let's just scroll down. Yes, everything is taken into account here. We push then here the matrix button, then the OK, and then we can close the wizard. And now you see everything pops up here in the workspace. So let's just recall this matrix. Let's call it capital Y underscore gross, okay? Because this is the gross return matrix, and we denote it as capital Y. So you see here the dimension, time series dimension is 351, and the column dimension is 25. 25 test assets, 351 time series observations. Let's also import the matrix of risk factors. Let's double click here again on import. And let's double click here on Europe risk factors small. And again, the wizard here opens. We don't want to have the risk-free rate here in our risk factor matrix. Okay, so we can just take it away. We just moved this with our mouse one column to the left. We don't want that. Moreover, what we see here is we have everything seems to be in the data set. We push on matrix. We have now our 5 risk factors here that we want to investigate. Push the OK button, and it seems here there is something wrong. Let's try. Okay, let's remove this again. Let's go again on import data. Double click risk factors, matrix. OK, and now it's imported here. You see. But we see here is that we have a 350 by 5 matrix. So we have only 350 time series observations. So we need to adjust somehow here. So we have obviously one row less observations. Again, this data set starts in July 1990. So it's obviously the last observation that is missing here. Yes, exactly. You see here the data sample ends in August 2019. So we have to adjust this matrix here y gross. So let's code it. Let's go into the command window. Let's code y gross. Let's denote. Let's define the matrix y underscore gross 1. What should it be? It should be the matrix y underscore gross. Now we have just replicated the same matrix. You see now the same matrix is copied but called as or denoted as y underscore gross 1. Yeah, it's the same matrix. So let's define the matrix y underscore gross again. Let's define it as y underscore gross and gross 1, okay, and let's take the observations, the rows 1 until 350, okay. Then we have to make this comma here. That means now we are on the column space, and we do this double point here, which means take all columns, okay. You see, now we have defined this new matrix y underscore gross that we want to operate with, and we can actually delete this matrix here from our workspace because we don't need it anymore. We operate with this matrix that we just defined. Okay, so we also need the risk-free rate. Let's import the risk-free rate as well. Again, it's here in this Excel file for the risk factors, and let's just skip the first risk factors. We take just the last column vector here. Again, we put the matrix button here, import, and now here you see it's imported as a 350 by 1 vector in our workspace, or at least it should be. Okay, let's do it one more time. Sometimes you have to do things twice here in MATLAB, who knows why. Let's do it one more time. Matrix, okay, and push it away. It is still not here. So something seems not to work out properly here. So one more time. It should be actually no problem to import this data here. Yeah. Okay, it's imported as Europe risk factor small. Okay, so we have to define it here. Let's define this as RF. That's our risk-free rate. And now you see, unfortunately, it has overwritten the risk factor matrix, so we have to import the risk factors one more time. Let's do it one more time. Let's skip the last column vector here, push a matrix and import. Okay, now it's imported. Okay, and now let's recall it here. Let's rename it as capital F for factors. Okay, so we see the time series dimension is correctly here for the factor matrix, 350 by 5. Yeah, we have 5 permanent French risk factors. We have the risk-free rate here as a 350 by 1 vector, and the gross return matrix of test assets that we want to test using the Fama MacBeth regressions. And this has the dimension 350 by 25. Okay, so our capital K is 5 risk factors. Our capital N, the number of test assets, is 25. Yeah, and our capital T is 350. So let's define first of all, let's go back to the script, and now let's define first the time series dimension, which is the length of our vector of the risk-free rate. But it doesn't actually matter. We can also write here in parentheses the length of the factor matrix, or the length of our gross return matrix, because the length, the time series dimension is always the same. But it's just keep things simple here. We define capital T as the length of our time series vector for the risk-free rate, which is 350. Let's also define the number of test assets, which is 25. Yeah, we know this already. The number of risk factors is 5. It's a permanent French 5-factor model. And let's now let's create a matrix where we want to store, you remember from our whiteboard derivation, the matrix sigma E, which is the covariance matrix of the residual vectors from our time series regressions. Yeah, we have to store the residual vectors of our time series regressions in a matrix, and this is what we do here. Yeah, let's define a matrix capital E. What should it be? It should be a matrix that has zeros, t entries, because we have t time series observations, and n, yeah, because we have n test assets. So in each column here of this matrix, E, yeah, each column, we store the corresponding residual vector of each time series regression. Yeah? So you remember, we start in the Fama MacBeth framework with the time series regressions. Yeah? And we have to store the residual vectors for each time series regression, yeah, in a matrix. This is what happens here. Next, we have to compound the, let's compound the excess returns. Yeah, again, we have to operate with excess returns. This is happening here. Let's do this. Let's create a matrix. Let's call the matrix capital Y underscore excess. Yeah, it's the excess return matrix. And what should it be? It should have the same dimension as our gross return matrix. That means capital T rows and 25 or capital N columns. Huh? It has the same dimension. So what do we do? Okay, let's compound a for loop here. We do something for I is 1 until 25. Yeah? Capital N is 25. So what do we do? Okay, let's say, okay, we take for, in each iteration I, we take the whole column I. Yeah, so if I, in the first iteration, if I is 1, yeah, we take the whole vector, so the whole vector of the first test assets, okay? If I is 2, in the second iteration, we take the whole vector of the second test asset and do something, yeah? So double point means take all entries, and since we, in this case here, we take all entries in the first column, yeah? So the whole column vector. What do we do? So in each iteration I, we subtract just the vector, the t by 1 vector of the risk-free rate. That's it. So that's what we do for all 25 test assets, and let's just do it correctly here. So we grab, so in each iteration we grab the corresponding vector of gross returns, okay, and subtract the risk-free rate. So now it's correct. Yeah. So again, in each iteration, what do we plug into each column I? So we plug in the corresponding vector of gross returns subtracted by the risk-free rate, and that's, as per definition, the excess return of an asset. So that's fine. So what do we do now? So you might remember from the lectures, the first step was what? Yeah. Remember now, the first step was what? It was to create the matrix, the capital B hat, okay? Create the matrix capital B hat. And we just keep things simple here. Let's just, this matrix that we denoted as capital B hat on the whiteboard, it's just here capital B, okay, for simplicity. So that's the beta matrix, okay? That's the so-called beta matrix, yeah? That is our regressor matrix in the second step of the Fama MacBeth regressions, okay? So what dimension should it be? So we know already from the lectures, it should have the dimensions capital N by K, yeah? So we define it as a matrix that has zeros, capital N by capital K, yeah? And always we have to, after each command, we plug in here this colon button, so that otherwise MATLAB would spit us out this guy here. We can do it just for fun. What happens if we plug in this into the command window and push the enter button? Okay, we have to plug in also this guy here. Let's do this. Let's plug it in here, and so that MATLAB knows what we are talking about. And now we just put in here this command. Yeah, you see this is what happens. MATLAB will spit us out what we just defined. So that's why we don't want to do that. That's why we push here, after each command, we plug in the colon button. So what do? Again, we have to operate with a for loop for I is 1 to capital N. So we do something capital N times. So what do? We know from the lectures on the whiteboard, we are doing simple OLS regressions, okay? Now let's define for each loop, for each iteration I, we define the vector of the excess returns of test asset I. What should it be? It's small y is equal to what? So let's grab the corresponding vector of excess returns of the first asset of asset I. So that's now the definition. We defined the corresponding vector of test asset here. We grab in each iteration the corresponding column in our matrix capital Y underscore excess from our excess return matrix. We define the matrix of our regressor matrix, and in the time series framework, okay? So how does it look like? So we have a vector of, now remember, we have an intercept term in the time series regressions, okay? So that's very important to remember. So we have to include it here as well in our regressor matrix. So, and that corresponds to a vector of ones. We have to have a vector of ones, capital T by 1, okay? So that's the command that gives a vector, that gives you here a vector of ones that has capital T observations. And then we add just our factor matrix here. And we know the factor matrix has the dimension, which is here denoted in the workspace. It's 350 by 5, right here. So our regressor matrix has the dimension 350 by 6, because we add here a vector of ones, okay? And this sign here, this means in MATLAB, create a matrix, okay? And what we put in here is one matrix and a vector. So this we have here in augmented matrix. Our capital X is defined as a matrix of ones that has ones in the first column, and in column 2 to 6 we have our risk factors. Okay. So next we do our simple OLS regression. We know the point estimator is defined as what? The regressor matrix. Let's do it here. Let's write it immediately. The regressor matrix transpose times itself. We have to invert this expression here, this matrix, times the regressor matrix transposed, times our vector of test assets. Very simple. This B that we get out here has the dimension 6 by 1, right? It must be 6 by 1 because for each regressor in the X matrix here, we have a point estimate. We have the corresponding exposure. And we know that the intercept term, which is the first entry here in our B vector, gives us the corresponding, or the part of the excess return from the test asset that is unexplained by the remaining risk factors. So what then? So we have to store. You might remember from the whiteboard derivation, we want to store these point estimates. We store it in this matrix B, capital B, that we here constructed before the for loop, and we denoted. So let's say in the first row, so row I, in all columns, what do we store there? So remember now, the dimension of our capital B matrix, it has in each row capital K entries. So, but our beta vector has one entry more, but we are not interested in the first entry, okay? Because this is the entry for the intercept term that we do not need in the second step of the Fama MacBeth regressions. We just need the exposures against the risk factors, okay? So what we do is we say, okay, grab the elements, the second element. We start at the second element, which is the market factor in excess form, until element k plus 1. We know the k plus 1 element in our beta vector is the exposure of the test asset y against the investment factor. Yeah. So, and we have to transpose this guy as well, right? Because this is a k plus 1 by 1 vector, yeah, and we want to store it here in as a row vector. So we have to transpose it. Yeah? So if we transpose a k plus 1 by 1 vector, it's a 1 by k plus 1 row vector. And so we store the elements 2 to 6, yeah, the corresponding risk factor exposures here in the first row of our capital B matrix. This is what happens here. Then what else should we have to do? Well, we know that we want to store the residual vector, yeah, from this regression. For each regression, we want to store the residual vector in this matrix E. So how do we do that? So we say, okay, all rows in column I from this E matrix should be what? It should be the residual from this corresponding regression. So it's test asset I minus the regressor matrix transposed. No, it's not transposed. So it's the vector y. So the excess returns of the test asset y minus the regressor matrix times the corresponding point estimate b. So that's it. So we do this for all 25 test assets. Yeah, very simple. So what's then the next step? Now we have defined the matrix where we have stored the residual vectors, and we have constructed this matrix capital B, which was in our whiteboard notation capital B hat. Yeah. So the next step was that we have to compound the covariance matrix of the risk factors. Yeah, but that's very simple. Yeah, we know already that we just have to plug in this command here in MATLAB, which is covariance from F, from our factor matrix, and it gives us the corresponding 5 by 5 covariance matrix. So that's not the big deal. So what we have to do is next is, so the third step from the whiteboard, what was that? It was obviously to compound the vector of expected excess returns. So we have to compound the expected excess returns from our test assets, How do we do that? So let's define this vector as capital EXP underscore ret. Yeah. This is our vector capital RET from the whiteboard. It's defined as zeros, capital N by 1. Yeah, because we have 25 test assets. And what should it be? Let's operate again with a for loop because it's so simple. For I is 1 until capital N. So each entry should be what? Let's copy it here. So each entry I should be the mean of the corresponding vector, column vector I in our excess return matrix, right? So this is in the first iteration, yeah, it would basically, now something is okay, we have to write here P, I wrote in O, so now it should be correct. So in each iteration I, yeah, it takes the mean, yeah, for the whole column vector. Yeah. If we go back to our matrix here, let's open the Excel file here. So in the first iteration, it would give us basically the average of the first column here, yeah, which are the excess returns for the first test asset. Yeah. So let's go back here. What was the next step? The fourth step from the whiteboard, it was to compound the risk premiums, right? So we have to compound the risk premiums lambda. Okay, so that was basically the fourth step, and it was defined as what? Lambda should be what? We define a vector, lambda, and we know now this should be a 5 by 1 vector, yeah, because we have 5 risk vectors. And it should be what? Yeah, we take our matrix capital B transposed times itself, inverted, right, times itself transposed times this vector here that we just created. Yeah. So that's it. And again, we know if we transpose this guy, it becomes a 5 by 25 matrix, yeah, times 25 by 5. So what we have here is a 5 by 5 matrix. And if we take the inverse of a 5 by 5 matrix, what comes out is a 5 by 5 matrix. Yeah? So 5 by 5 matrix multiplied with a 5 by 25 matrix multiplied with a 25 by 1 vector, what comes out is a 5 by 1 vector. So this was the fourth step of the Fama MacBeth regressions. What is the fifth step? What was the fifth step from the whiteboard? You might remember that. Hopefully you have your reading notes ready. So the fifth step was the covariance matrix. What's the covariance matrix of our lambda? Yeah. So this was basically the question. What's that guy here? Yeah, so we have to define this guy as well. And we know it's a n by n matrix. No, sorry, this is a 5 by 5, this is a k by k matrix. Yeah? This is a k by k matrix because we have k risk factors. But you might remember from the formula, this was a very long formula, that we need the matrix from the residual vectors, which we have here, capital E. Yeah, we have already the matrix defined here. We have elements in this matrix, and we know already that in MATLAB we just have to define, we get the covariance matrix from a matrix by just plugging in cov from that matrix. Yeah? So that's basically what we have to define. So and now we can also define the matrix, the corresponding covariance matrix of the risk factors. We do it now both at once. So let's define sigma, which is the covariance matrix of our residual vectors from the time series regression framework. Let's define it as sigma underscore E should be what? It should be the covariance from E. Yeah, very simple. Next, we define our sigma, the covariance matrix of the factors, sigma underscore F, capital F. What is that? It will be cov from F. Yeah, very simple. So then let's implement this huge formula. Yeah, so we want to know what is the sigma lambda, sigma from the lambda. This is what we are interested in, the covariance matrix of this guy here. And now you remember that we want to implement the so-called Shanken correction here as well, in order to account for the bias, because in the first step here, the betas are estimated, okay? And that's what the Shanken correction basically accounts for. So you might remember now from the whiteboard this long formula. Yeah? It starts with 1 over capital T, and then we have this expression in the parentheses. Yeah? So let's plug it in here let's translate this formula into MATLAB language. So we have to start with capital B transposed times itself. This guy was inverted, yeah, you might recall from your lecture notes, times capital B transposed times sigma from what? From our residual vectors, the covariance matrix from the residual vectors that we have defined here. Sigma underscore E times what? Times our capital beta matrix, where we have stored the factor exposures, the beta estimates from the first pass of the regression, times what? Times again beta transposed times itself inverted, times what? And now we plug in 3 dots here, which means we continue with the same formula in the next row. And now we have to define the Shanken correction. So this part here, what we have defined here, is the gives us the standard, the simple covariance matrix. But we also want to account for the standard for the Shanken correction. So and it was what? It was 1 plus lambda. We have to take our lambda vector again and transpose it, so that it becomes 1 by k vector times what? Times this sigma times the covariance matrix of the risk factors. And we remember this guy was inverted. So times lambda, and now we can close this parenthesis. So what we have here, that's the Shanken correction. Okay. So now we have to add the covariance matrix of the risk factors, which we denoted here as sigma underscore f. Recall that from your lecture notes. So and then we can close the outer parenthesis here, okay, which happens here, and we have to divide. We have to multiply it with the factor 1 over capital T, which means in essence just that we have to divide it by capital T. So remember now, this is the covariance matrix, so that's a 5 by 5 matrix, okay, and we are interested in the elements on the main diagonal. So the 6th step from the whiteboard derivation was what? It was compounding the T statistics. And that's just grabbing the elements from the, we grab each element from here and divide it by the corresponding element here from the covariance matrix. So let's do that. Let's just copy everything here into MATLAB. Let's press Ctrl-C and copy it here into our MATLAB, into our command window. So now everything happens here in the workspace. Okay, let's just check what is lambda. We can copy it here. So that's our point estimates here. Okay, that are the risk premiums, and let's also let's now get the T statistic for the risk premium, for the first risk premium here. Okay, which is the which is the market factor in excess form. It's 0.45% per month. So let's take the first element here. Let's take the lambda 1 and divide it by what? Divided by the element 1, 1, or by the square root, by the square root of the element 1, 1 in our from our matrix sigma underscore lambda, which is a covariance matrix. So we see the excess returns of the market factor accounting for a Shanken correction here has a T statistic of 1.74, which means that the market risk factor is marginally priced in the cross-section of expected returns using 25 test assets sorted by size and profitability. Okay, we can also do the same for the second risk factor, which is the size factor. Let's grab the second element of the risk premium vector lambda and divide it by the corresponding element, the second element of the main diagonal from our covariance matrix. This is what happens here, and we see the size factor is not priced. The T statistic is below 1.96, which implies the size factor is not priced in the cross-section of expected returns using 25 test assets sorted by size and profitability. Let's also check the value factor, which is the third column in our factor matrix. Let's grab the third element from the risk factor, from the risk premium vector, and divided by the corresponding square root of the third element on the main diagonal of the covariance matrix for the risk factors, and we see the value factor is not either priced. Yeah, that's interesting. What about the profitability factor, which is the fourth factor? Let's grab the fourth factor from our risk premium vector and divide it by the corresponding main element on the main diagonal. Yeah, we take the square root out of it, and we see the profitability factor has a cross-sectional t-statistic of 6.76, yeah, which means this is statistically significantly priced on any level. Yeah, so the risk premium of our that is corresponding to our profitability factor, which is here 0.82% per month, yeah, is statistically priced. Yeah, this is what we figured out here, even after accounting for the Schengen correction. And we see, let's also take the last factor here, which is the investment factor. Yeah, let's grab the fifth element from our risk premium vector and divide it by the fifth element, the square root of the fifth element from the main diagonal from our covariance matrix for the risk premiums, and what we see is it is statistically not priced. So in sum, we see that the market factor is priced, but only marginally on the 10% level, but the profitability factor seems to be the only factor that is priced in the cross-section of expected returns using 25 test assets sorted by size and profitability. Yeah. So what else can we say? So we know that the Schengen correction accounts for the uncertainty in the estimates, but often, or sometimes, let's say at least sometimes, you will find that the Schengen correction is not accounted for. Yeah. So let's copy everything here into here, and let's do here this percentage sign, which means that MATLAB considers this as a text and not as a command, okay? And let's just neglect from the Schengen correction. Let's just take this away. Let's delete the Schengen correction. Let's re-estimate the sigma, this covariance matrix. Let's do this again. And let's once again see how the market factor is priced now. If we do not account for the Schengen correction, again, we copy this argument here, this command, and what we see now, if we do not account for the Schengen correction, we see that the market factor is priced. Yeah. What about the size factor? Let's check the size factor. We see the size factor is not priced. It's still not priced. Value factor, what happens here, is also not priced. And what we'll see now is probably that the t-statistic will dramatically increase. No, it's not the same. That's actually quite funny. So we see that the t-statistic is actually exactly the same. Yeah, irrespective of whether or not we account for the Schengen correction. That's actually quite interesting. And I believe for the investment factor, it will be still the same. It will be statistically not be different from 0, and this is exactly what comes out. Yeah, so we see obviously the risk premium that is related to the profitability factor is the same, but we see the difference is here obviously that the market factor in excess form becomes significant if we neglect from the Schengen correction. Okay, let's go back here. Let's take this away here, our small experiment, because we want to have the Schengen correction in, so we have to code it now once again, the Schengen correction. So it was 1 plus lambda transposed times what times sigma underscore f, so the factor matrix from the covariance matrix of the risk factors, and this guy was inverted times the vector of risk premiums. Yeah? So that now we have it again here. So that was the t-statistics. Then this 7th step was okay. we wanted to investigate, is the model correct? Is the model correct? So, and what were we supposed to do? We were supposed to compound the alphas, yeah? So the pricing errors. You might remember that from the whiteboard derivations. We have defined the pricing errors, alpha. We have to, what are the pricing errors of that Fama MacBeth regression framework? So we have defined it as alpha. So let's just code it here. Let's define the pricing errors alpha. And we know we have 25 test assets, so this guy must be a 25 by 1 vector, right? And it's defined as what? Yeah, we have to subtract from the vector of expected returns, and that's defined as this guy here. Yeah, we have to subtract the estimated expected return, and that's defined as our capital B. It was on the whiteboard capital B hat, okay, times the risk premium vector. Yeah. So again, what's happening here? We subtract from the factual expected return vector the estimated expected return vector, and that's per definition the error, yeah, and it's in this context called the pricing errors, and we know it as alpha. So we have to define the the 8th step from the whiteboard. It was what? It was the test statistic. We have to implement the test statistic, and we also know that we have to define the covariance matrix for the test statistic. We have to define the covariance matrix from this alpha. Okay. So that's basically what we have to do in the 8th step. We have to define the covariance matrix of the pricing errors, and that is defined as covariance. Let's define it as covariance underscore alpha. And what should that be? You might remember that we have to start with the identity matrix, and it's defined as, you just have to define I from capital N. If you define I from, in parentheses N, MATLAB will spit you out identity matrix of the dimension n by n. Yeah, this is what is happening here. Okay, you have 25 by 25 matrix, and you have on the main diagonal just once. Okay, very, very simple. That's why MATLAB is so easy, so user-friendly. Yeah, so we have to subtract this expression here, capital beta times what? Times beta transposed times itself inverted times beta times capital B, sorry, transposed. Yeah, you might compare this with the derivation from the whiteboard. Then we have to subtract, we have to multiply this expression by what? With the covariance matrix sigma E, yeah, for the residual vectors from the time series framework, which is defined as sigma underscore E times what? Times actually this expression here that we have here already defined, but this guy here, this expression needs to be transposed, right? Yeah, so this needs to be transposed. So then we close this parenthesis here. You might remember from the whiteboard we have to divide this by capital T, and we have to multiply this expression with the Shanken correction, which we have already defined here above. So we just can copy this. Okay. Copy this here and take away this one parenthesis here because we don't need it. So that's now we have to define the corresponding covariance matrix of our pricing errors here, and now we can implement the corresponding test statistic. We know the covariance matrix is a capital N by capital N matrix. It's a 25 by 25 matrix. So it must be like that per definition. And if you go through the dimensions of each matrix here, yeah, you will figure out that what comes out here is a 25 by 25 matrix. Yeah, let's copy this into the command window. Yeah, everything seems to be all right. Let's go here into the workspace, let's have a look at this matrix here, and you see it's a 25 by 25 matrix. Let's double click on covariance underscore alpha, and here what you see is the corresponding covariance matrix 25 by 25 for the pricing errors. Okay, so let's go back here. Let's implement our test statistic. So the test statistic, let's define it as test underscore stat underscore alpha, and it is defined as what? It's the alpha, the vector of pricing errors, times what? We have to transpose this guy so that it becomes, because we want to have a number here, right? The test statistic must be a number, so this guy is a 25 by 1 vector. It becomes, if we transpose it, it becomes a 1 by 25 vector, okay? We multiply this guy here by the inverse of our covariance matrix for the pricing errors. Yeah, take the inverse here and multiply it again with the pricing errors. And we know this guy here is under the null hypothesis distributed with capital N, that's distributed with capital N minus k degrees of freedom. Okay? If the null hypothesis is true. And it's distributed as the chi-square distribution. So let's just plug this into MATLAB here, copy it into MATLAB, and let's see what comes out. So we see that the test statistic is 53 times 26. Yeah. So, and under the null hypothesis, we have to compare this guy here with the corresponding critical value for the chi-square distribution of 20 degrees of freedom. And that's what we can do. We can basically grab statistical tables, yeah, and compare this value with the corresponding chi-square distribution with 20 degrees of freedom. If this value here is above the 95% critical value, then it means obviously that we have to reject the null hypothesis. Yeah. So let's see what is the critical value of the chi-square distribution with 20 degrees of freedom. We can just open here a new window. Let's go for chi-square distribution table. We can just Google it here. We can just here grab one of these tables here. We see, let's open that. No, we are no, we don't need that. Let's go here. So here we see a chi-square distribution table, and we see here that's the critical value that we need, the 5% critical value. So this means that 95% of the probability density for the chi-square distribution ends here. If we have 1 degree of freedom, it ends here. Yeah? So whenever the corresponding test statistic exceeds this value here, we would reject the null hypothesis on the 5% level. So, but we have 20 degrees of freedom, right? So we have to scroll down. It's here. So we have this third column from the end, and 20 degrees of freedom we have here. So 31,41. So if our value exceeds this value here, we reject the null hypothesis, which means that our pricing model is incorrect. It cannot price the 25 test assets sorted by size and profitability. And we know that the value of our test statistic is 53.26. Okay? This value is larger than what we have here, than the corresponding value here, than 31.41. So this means we reject the null hypothesis on a 5% level. Yeah? So this means that our pricing model, yeah, the Fama and French 5-factor model, is not able to price these test assets, our 25 test assets sorted by size and profitability correctly. Yeah? So that's basically how we would implement this test. And by the way, if MATLAB spits you out here something like this, matrix is close to singular or badly scaled, what we can do then is we can use the pseudo inverse. So instead of taking the inverse here, what we can do is we can command in MATLAB the so-called pseudo inverse. It's denoted as PINV. It takes the pseudo inverse of something. We can repeat this test. Let's with the pseudo inverse of our covariance matrix. Yeah, let's do that. Let's again copy this into the command window. Let's see what comes out. If we take the pseudo inverse, as you see, if we take the pseudo inverse, the test statistic becomes even larger. Yeah, so our conclusion doesn't change. We still reject the null hypothesis on a 5% level. Yeah, even if we would take a higher, even if we would take a 1% level, you see, we would even reject it at a 1% level. Yeah, this irrespective which significance level we choose out of 5% or 1%, it doesn't change our conclusion. We reject the null hypothesis, which means that our pricing model, the Fama and French 5-factor model, is not able to price this test assets correctly. So one last thing that I would like to discuss briefly. So the point is that the Fama MacBeth framework, and anyways any kind of regression framework, is only defined if the data that we use, if the variance of the variance exists. So we have to make the strong assumption, yeah, in order to use this methodology, we have to assume that the kurtosis of our data vectors does exist. Yeah, so we know from finance that many test assets or that stocks, they typically have a kurtosis that is much larger than 3. Yeah, so what we actually were supposed to do is we have to ensure, or we have to test if the variance of variance or the kurtosis, yeah, does exist for all test assets and also for the risk factors. Otherwise, this method would be sample specific. Now, this is something that you might need to know because in many studies, people employ this methodology and they report numbers, either significant or not significant, but in the end of the day, if our data suggests that the input data is not normally distributed, then we have some problems here with statistical inference. Thank you for your attention.